Hello and welcome to the Making a Model Organism Database webinar series, Part 1, Building the Database. I'm Alexander Shearer, speaking for the Bioinformatics Research Group at SRI International. And in this two-part webinar series, we're going to walk you through using our desktop Pathway Tools application to make your own model organism database off of any annotated genome. Now, as I mentioned, this is a two-part webinar series. In Part 1, this part, we're going to cover what you need to build a database and then using Pathway Tools to actually make your database. In Part 2, we'll cover refining your database and editing your new database. There are just a few things you need to make your own model organism database using Pathway Tools. First, you need an annotated genome. We don't handle annotation. Basically, all you need is a GenBank file and a FASTA file that goes with that genome. Or GenBank files and FASTA files plural in case your genome has multiple contigs, multiple chromosomes and a plasmid, etc. We can handle all of that. Then you'll need the Pathway Tools software with editor and pathologic. Now you can get the Pathway Tools software for free if you're an academic or government user from our website. To get the software, you'll have to sign a license, but again, it's free. You'll just sign the license, someone from our group will contact you, and you'll be able to download the software. Let's take a quick look over at the website to show you where to look for that information. This is the BioPsych homepage, and if you're interested in looking around and finding the kind of software download you'd like, you just go down here on the left, down to Software Data Download. Just click on that, and it will bring up information about what you can download, everything from flat files that just contain the data to the full software setup that you'll need if you want to make your own model organism database using Pathway Tools. All the information is right there, and you can email us if you have any questions about specifically what you need to download. Right now we have versions of Pathway Tools that are available for Unix machines, Linux machines, and Windows machines, and we've actually successfully run the Windows version on dual booting Intel Macs also. So once you have your copy of Pathway Tools installed on your local computer, then you can go ahead and make model organism databases just like I'm going to do in this webinar series. So once you have the software and a genome and the files for that genome, you'll stick them all together, and what will you get out? Well, you'll run that genome into Pathway Tools, and out of it you'll get predicted metabolic pathways, predicted operons, predicted pathway hole fillers, predicted transport reactions, and an editable model organism database for your organism of interest. Now let's look at that in a little bit more detail. Here's how Pathway Tools actually works, and then again we call this subset pathologic, that part that figures out how to make a database out of your annotated genome. What happens is you stick your GenBank files and your FASTA files in, and the software first identifies all the genes and identifies when there should be gene products of a given type, an RNA, a protein, that kind of thing. Then enzyme functions are drawn from the annotation. And this is an important point because our initial set of enzyme reactions are based on what your annotation says is there. We're name matching. So if you, for example, say that you have some kind of glucokinase there that we have in our large array of reactions in the Metapsych database, which is what we're referring to, then we'll predict that, we'll add a frame for that actual reaction, we'll add links to the original protein, etc. And one of the upshots of this is that if you go through this whole process and you come out with very few predicted reactions, even though you have a big genome, you want to go back and look at your annotation and see if the GenBank file that you're pulling from uses the format correctly. If it does something weird in how it identifies the products, there may be something we need to hard code around, because we find different groups have different ways of using the fields in a GenBank file, and not all of them are parsable by our software right now. It may also just mean that you have one of those genomes that doesn't actually have a lot predicted for it. If you have just waves of hypothetical proteins, we can't do much with that. But ideally, you'll get a good set of reactions out, and that'll be step one. And then in step two, we predict pathways from the predicted enzymes. So we've gone through your genome annotation, we've pulled out the reactions that we think are there based on which enzymes the annotation says are there, And then we're going to predict metabolic pathways. So for example, if we see 3 different enzymes from the TCA cycle, we're probably going to predict the TCA cycle. Now, the entire prediction process I'm not going to go through in detail in this webinar. You can read about it in some of our publications. We attempt to avoid some false positives, but we err on the side of predicting a little bit too much instead of a little bit too little, because it's better for us to guess about things that are there than have you edit it out later, instead of underguessing and maybe cutting out some results that you wouldn't have thought of but that are very important. So once we have these pathways predicted from the predicted enzymes, then we can go ahead, we can predict operons, or more properly transcription units. And again, how that's done I'm not going to go into, but that's described in our publications. Then we predict transporters, looking at the annotation and looking at some of the details in the transcription units. Then finally, as a big and important refinement process, we predict pathway hole fillers. So for example, I mentioned above, if we found 3 enzymes in the TCA cycle, well obviously if we found 3, we've missed a lot of them. And it may be that they just weren't in the annotation. Sometimes it's because of, as I said, quirks in the annotation and they're really there but there was a typo. Once you really start using software that depends on genome annotations, you'll notice how many typos there really are in an average GenBank file. But so we have, say, our TCA cycle with 3 enzymes in it, with like good guesses at what the others are. And so we have an entire software package, the pathway hole filler, that makes those good guesses. And again, I won't go into the details, but it uses a number of mechanisms to pick high-scoring genes that seem likely to code for different steps in those pathways. And you can go through and manually evaluate all of those results, or if you're doing a lot of these, you can go through and just set a cutoff and accept all the things above the cutoff, which is what we do for our biosite collection. So this will fill in additional guesses, and this is one of the ways that this is useful not just for making a model organism database, but also for helping in a genome annotation, because you can imagine a process by which you do an initial genome annotation using normal genome annotation tools, then you run it through pathway tools, and you run it through pathologic, and you run it through the hole filler, and you look at what was predicted in the hole filler step and go back and add those predicted functions to your annotation. So it's not just a tool for making a database, but it's a tool for annotation refinement also. Okay, so that's the overview of what we're going to do. Now why don't we go ahead, grab ourselves a genome, and get started. Okay, so here we are at NCBI's page that lists all the completed annotated microbial genomes that have been publicly released. Now, there's 566 completed microbial genomes as of today. By the time you're viewing this webinar, that number will almost certainly be higher because they're coming out about 1 every 2 days. And this makes it especially handy to have a way to just throw a genome at a piece of software and come out with a database. Now we're going to take the second one from the top here, sequenced and annotated by Collaborating Institute, JCVI, and that's Coxiella burnettii Dugway 7E912. And that just rolls off the tongue, doesn't it? Now, before we do anything with the files, even downloading them, we need to tell the software that we want to make a database. So let's go start up our pathway tools and take a look at how we do that. Okay, so here we are. I have Pathway Tools version 11.5. Keep in mind that if it's been a while since this webinar was made and you're looking at it, you may have a more recent version with additional capabilities. I have the Windows version that I'm running here, and I have the what we call the NavEd Path Tier 1, Tier 2, which is a very complex way of saying that my version has the navigator, has the editing function, and has pathologic, so I can actually make new databases, which is what I'm going to do today. And I have both the Tier 1 and Tier 2 databases. So once again, our Tier 1 databases are EcoPsych and MetaPsych, which MetaPsych is our big resource that lets us do the kind of predictions we do to make a database. And then I have a bunch of other databases that I won't actually be using, because of course what I'm doing today is making my own new database. So to get started making our own database, let's go to Tools and click on Pathologic. And that pulls up this pathologic window that tells us that we don't have an organism selected and that there's nothing going on. With that in mind, let's go over to Organism, create new. And we get this window. Okay, so what do we absolutely need to put in? Well, we need an organism or project ID. And we're looking at Coxiella burnettii, so let's go with cburn as our project ID. We can have a version. In this case, it is 1.0 by default because we started. You'll notice it named it project ID psych for cburn psych. Full species name, Coxiella burnettii. And again, it conveniently abbreviates that in the appropriate fashion. And then the strain, if we want to, this is actually entirely optional, but we're going to put it in Dugway 7E912. As I said, rolls right off the tongue. You can put in the taxon ID. Something that is less optional is to put in the phylogenetic classification. You don't have to do it, but it will help with avoiding certain weird predictions that we might want to avoid. So let's go down here, click down, and we're looking at a proteobacteria, so we'll click on that. But you can see we have a whole bunch of options. Then we have the codon table. In this case, we're going to go with the let's go with the bacterial codon table, which is the same as standard except for alternate initiation codons. But we have mitochondrial tables, we have lots of tables. Now, here's just lots of additional space to put stuff in. We can have institution types. We can have citations up top if you have a publication with the sequencing in it and you want that to be a top citation. We have a footer citation that will go on each web page. You know, we do this on our database. You can also do the storage type, file or Oracle or MySQL database. We're going to stick with file for this example, and there's a good chance that's what you'll be doing when you do this yourself. Okay, so we've put in the basic information we need. We just scroll down here and say OK. Now this is talking to the SRI server to get a unique ID for this. As you can see, today we were able to talk to our server, which is good, given that I'm sitting very near the servers. But on the chance that you're not connected that day, we're not connected that day, it'll go ahead and assign you your own ID and not worry about it. We just like to assign unique IDs because later you might want to upload it to our registry, and then it would be good if there were no overlap, but it's not a big deal. Okay, so what it's done is it's gone through and generated what we'd call the skeleton of a pathway genome database. It has a bunch of the hierarchies, it has all the things you're going to layer the data onto, and at this point you don't need to worry about that. And what you actually need, and it will tell you what you need the sequence file or files, you need the annotation file or files, and you need a file geneticelements.dat in the database directory that is now made in your ptools local folder. And so let's start with downloading the sequence files that we need and the GenBank files. So we're going to start by downloading the GenBank and FASTA files that we need to make this database. So let's skip back over to the NCBI site. Once again, here we are in the NCBI site. I am just going to go through and click through on the Refseq link. And this brings up the Refseq page. I'm going to scroll down for a moment because I want to show you one thing that's important, which is that the topology here is circular. This will matter because we're actually going to ask you a little bit later when we edit the genetic elements file whether your chromosomes and things are circular or linear, which just has to do with how we represent them mainly, and will affect a few other things. And here I'm going to click through to the GenBank FTP. And here we are on the FTP directory for Coxiella burnettii, Dugway, etc., etc. The organism that we're intent on making a database for. This can look a little bit confusing, but remember, you only have to look for 2 files per genetic element, and right now we're looking for 2 genetic elements, 1 chromosome, 1 plasmid. And just scrolling down from the top, the only 2 suffixes we care about are .fna and .gbk. .fna is the FASTA file, .gbk is the GenBank file. And you can see here we have a big GenBank file, 4.7-ish megs, and we have a little GenBank file. You can guess we have the chromosome and the plasmid there. You may occasionally need to open these files to figure out which is which, or if you have an organism with maybe 3 plasmids. These directories are not always as clear as they could be. Okay, so let's just start downloading and saving files. So we'll just start saving the files we need one by one into the appropriate directory, starting with the FASTA file for the whole genome. So I'm just going to right click on that, save link as. Okay, back up to the desktop for me, computer, C, documents and settings, your username, and this is all on a Windows machine. This may work differently for you. You'll just want to look at where it told you it put the appropriate folder, and it told you that back on the pathologic page that we started on. I'm going to Application Data, ptools local, PGDBs for Pathway Genome Databases, User, cBurnSeq. Then 1.0, Input. Okay, now here is the folder where we're dumping the 4 files that we need. You can see already in there we have an organism.dat file, an organism init.dat. We're not going to mess with either of those, and a sample genetic elements dat file, which we will be editing once we finish downloading all this stuff. Now you could just save this thing with its given name from NCBI, but I find that really confusing. So I recommend changing it. So we'll just call this chrome1.fna because it is the first, and in this case only, chromosome. Okay, so we have our first FASTA file ready. Let's get the GenBank file for the genome. Again, I'm going to call it chrome1.gbk. You can see the FNA is there. Now we have the plasmid, and we'll call this plasmid1.fna. That was fast because it's tiny. And let's get the GenBank file here. plasmid1.gbk. Sounds good? Done. Also very fast. Okay, so we're done downloading what we needed from NCBI. We have a GenBank and a FASTA file for both the chromosome and the one plasmid that Coxiella burnettii, this strain anyway, contains. And now what we need to do is go to that sample genetic elements.dat file, turn it into a genetic elements.dat file, and edit it to point to the genetic elements we just downloaded. And don't worry, it's nowhere near as complicated or annoying as that makes it sound. So let's go take a look at that file. Okay, so I've gone ahead and opened the sample genetic elements.dat file, which was living in the same input directory that we just stuck those 4 files in the WordPad editor on my Windows machine. I recommend using the simplest editor you can for this, just so your WYSIWYG, complex, nifty text editor doesn't accidentally add in a bunch of invisible tags that will be really visible to our software and will cause problems. So we have a full set of directions here telling you everything you need to know. I'm not going to linger on them, but they're there. Read through them when you're actually doing this yourself. It tells you what each little thing is for. So a quick review: ID, you're just identifying the genetic element. A name, it's a descriptive name. The type, the 2 types we're going to care about right now are chromosome and plasmid. And the default condition is chromosome, whether it's circular or not. What codon table to use. So for example, if you were doing a eukaryotic organism and you would set the general codon table to whatever it is, but you wanted the mitochondria to naturally have the mitochondrial codon table, you can do that. A link to the annotation file, that's the GenBank file. A link to the sequence file, that's the FASTA file. You can get away without having this, but you might as well have it. And the contig file if you're actually using contigs and not, say, chromosomes and things like that. So let's scroll down. And we have a bunch of test things filled out ahead of time depending on what kind of conditions you might have. I'm just going to delete the ones I don't need right now, but again, I suggest that you just look through everything when you're working on this. Then I will copy the one that I'm going to use here and duplicate it. And now let's go ID. So the first thing is going to be just our chromosome. And we'll just call it chromosome because we just have the one. Name, we'll just go with chromosome. The type is indeed chromosome. Let's change this because it's circular. And now we went with Chrome1 as the name here, even when I saved them. But of course it's not a PF file. And if you're wondering what PF is our sort of homemade annotation format, pathologic format. And that's what we actually convert things into when we do our big biopsych builds where we're doing 100 things at a time, because it lets us sort of pre-filter to make sure that we can actually parse all the stuff we're working with. But we don't need to worry about that now, and you don't need to worry about that when you're working at home. So it's just the GBK. And then FSA is one possible suffix for a FASTA file, but in our case they're called FNAs. Then our second genetic element is our plasmid. We just have the one again. And we can change the name to the evocative name plasmid. And the type is obviously not chromosome. It is, in fact, according to the comments above, plasmid. Now, if you're wondering where I got that change from, let's click up here. And you can see under type, types are chromosome with this sort of chirism thing, plasmid, and MT for mitochondrial chromosome. So it's a plasmid. Yes, it is also circular. Its name for the annotation file is plasmid.gbk. The sequence file is plasmid.fna. Okay, so we have the information we need to point the software to the right places to look. So now let's save this, but we don't want to really save it into the sample genetic elements. We need to save it as something else. So save as just geneticelements.dat. And we're good with it just being a text document. We save. So now we have geneticelements.dat. We can get back to the process of actually making our database. Okay, so we're set. We have our files. We have our geneticelements.dat file. What do we do now? Well, at the bottom of the page, the software is telling us we can either do a trial parse or we can go directly to the build. Might as well do a trial parse. It lets you know if you've made a general mistake that will prevent an actual build. So we go up to build, click on that, trial parse. It'll ask you if you want to do any one of your genetic elements or all of them. Let's just select all and hit parse. Aha! So we have a problem. Now if you were watching carefully at home, you'll notice that I left something out when I was saving the file names, because even though we just have the one chromosome and the one plasmid, I numbered them both. Oh no, a mistake. This is why TrialParse is handy, because it's not going to go through a bunch of work and then spit up at you. It's going to spit up at you right away that there's a problem. So let's dismiss this, and I'll go edit that mistake and then come right back. Okay. Okay, that example is admittedly a little cheesy, but that's one of the values of trial parsing. It tells you if there's a problem. And you can see while I was away, editing my genetic elements.dat file, it actually went through, parsed what it could, told us, hey, I found some genes, I found some proteins, I found some RNAs, and I didn't find any of that plasmid stuff you were talking about. So once you edit your genetic elements.dat file to get it to work, you'll need to get out of the TrialParse and then try it over again. So let's try that over again. Build, TrialParse. Let's just do the plasmid, parse that. Okay, TrialParse is done, and it told us, why yes, I found 67 genes that make 67 proteins on your plasmid. And one of them was matched with the enzyme name matcher. So not a lot of enzymes on the plasmid, but a lot of proteins. Great, so now we're ready to actually build our database. And what building entails is going through the GenBank files and pulling out of that gene names, gene products, functional information, adding enzyme reactions on, all that stuff that I talked about before, and layering it onto that basic skeleton that we made at the very beginning. Okay, so let's do that now. Build, automated build, and it's off. And this is the part where it's not going to take that long, but you could certainly walk away from the computer if you wanted to, or you can sit here and stare at the screen as it tells you that it's found some ambiguous EC numbers that it doesn't feel like trying to match, and that it's now matching enzyme names. In general, I don't sit around and watch these reports, and you don't have to either. It's actually logging all this, so you could go back and take a look at it if you really cared. Of course, you'll just see the results in the final product. And you'll notice here it talks about pruning out variant or likely false positive pathways. And what that means is that, as I mentioned, we don't want to overpredict too much. So in this case, say variant pathways. If you look in Metapsych, we may have 5 different versions of glycolysis, for example. We don't really think your organism is going to have all 5, but there's a good chance there's heavy overlap between the different reactions in the different glycolysis pathways. So we predicted all 5, say, or all 3, or all 2, and then we're going to pick the best we can, the best one, or maybe 1 or 2, out of that set and dump the rest. Similarly, there are other ways we have to detect likely false positive. These are discussed in the publications. Okay, so now we're going to let it update the overview graph. That can take a little while, though not usually too long, and we'll come back when it's done. Okay, so we've generated an overview, and now we have a bunch of things we can do. It's actually going to tell us some of the possibilities: assign probable enzymes, rescore pathways, assign modified proteins, create complexes, and run the consistency checker. What we're going to do right now is save this. So up to Organism, save KB, and KB is knowledge base here, which is another way of saying database. So let's save. Okay, our database is saved. We have a rudimentary model organism database now. So let's click here and exit. Now, I clicked home there just to refresh this overall organism menu. And now you can see we've added our Coxiella burnettii Dugway 7E912 database. Our summary tells us we have 140 pathways right now. We have a little over 2,000 genes. A lot of citations, those are pulled in from Metapsych, so let's click on that. Here's our overview: 737 enzymatic reactions, 2,140 polypeptides, etc., etc. Let's go to Overview and show the cellular overview. And there we go. There is the state of our cellular overview right now. Now this is actually going to change as we make more modifications to the database, because right now we've predicted reactions and we've predicted pathways, but we haven't done anything else. So let's go back and refine. Tools, again, pathologic. Note that our database is still selected, and it's going to stay selected as long as we keep the application open until we tell it to pick a different database. Refine, assign probable enzymes. Okay, so what this does is it pulls up a list of things that it thinks are enzymes, but it couldn't be exactly sure. And often what will happen here is we have, for example, something that says, hey, this ends in ACE. That sounds like an enzyme. Is that an enzyme? Can you assign it? And you can see here, well, these are just called acetyltransferase, some family. We probably can't assign those. But this is 2-polyprenyl 6-methoxyphenyl 4-hydroxylase. We might be able to assign that. So what you do is you go through these things one at a time, left click on it, and you get this probable enzyme status dialog. Now, what it's going to do is it's going to say, sometimes it'll just be saying, I don't know, but this seems like an enzyme. Sometimes it'll do this. Hey, I think it might be this. Is it this? Is it this? And we're going to say, yeah, it's that. So let's assign that. And it shows you a little bit of the protein frame. You'll see a little bit more of this later when we go to editing. And you can say, okay, yeah, that looks good. Okay, that looks good. Boom. Now it's assigned. And so we can continue running through and doing the same thing. Assigning. Yes. Okay. And we have, in this case, 143 of these that we can assign. So let's look at this thing, this acetyltransferase GNAT family. We can say, there's no thing I can assign it to. Notice there's an assignment comment here, so when I make the assignment I can write a little note about it for later to remind me, why did I do this? So I can say, in this case, this is not a specific enzyme, I can't assign it. So, okay. And boom, that blanketed all these because they were the same name. Acetyltransferase family protein, kind of the same thing. You're going to hit a lot of these non-specific things, and again, that's purely a function of the annotation. So if you did the annotation, it's your fault, and otherwise it's just you're relying on what the annotators put in. You know, so you have a number of options. Let's pull that up. In addition to just picking one of the reactions that it's guessing at for you and saying sure, you could also freely assign it to a reaction that's already in the database or even pull something in from Metapsych. But I'm just going to click yes here, assign, and when it actually brings up this window, you can put in things like citations. So if you're sitting here with a stack of literature or with PubMed open in your browser and you're looking through on a protein by protein basis as you do this and finding literature that supports this, your annotations, your links, you can include that right here. And there'll be, again, a little more on that in the second round of this webinar series where we talk about editing. Okay? So basically, you just run down the list, do this kind of thing, and of course I'm skipping around like mad here, but you can do it whichever way you like. And I am going to exit. Actually, I'm going to save the KB first. Then I'm going to exit. I'm not going to run through all these right now, but you can do this. You can always come back and do this later for the things that haven't been assigned. So let's exit now. And it's going to save again on the exit. There we go. Okay. I made some changes, so I may want to rescore the pathways. So refine, rescore pathways. Let's do that. So what it's doing now is I may have added in some new enzyme activities, which I did, and I haven't taken any out, but this may affect whether or not our software believes that certain pathways are more or less likely to actually exist in your organism. I made very few changes, so probably there's very little difference, but I'm going to go ahead and do it by way of example now anyway. Okay, so that's done. Additional refinement. So we've made the database, we've assigned probable enzymes, some of them at any rate. Refine. What else do we have? We can assign modified proteins. I'm not going to do that now, but that'll let you put in things like a phosphorylated state of a certain protein, create protein complexes. This is an important thing to do if you have a lot of data about protein complexes in your organism of interest, because we don't predict very many protein complexes at all. If you were noticing when we went through the summary screen, for Coxiella here we have 4 predicted. And that's basically because there's usually not a lot of information with which to predict protein complexes looking just at the genome annotation file. The annotation typically doesn't support it. We could rerun the name matcher. I'm not going to do that, but that would look again at all the enzyme names, or the protein names rather, and see if it thinks any of them are enzymes. We can rescore pathways, which we just did. We can predict transcription units. We're going to do that now. Our next step after this is predicting transporters, or actually identifying transporters. And first we want to do transcription units. So let's start with that. Click on that. Select for TU prediction. We're going to select all because we want to predict transcription units both in the chromosome and in the plasmid. And we click predict, and it starts. Okay, and now we've predicted transcription units. You may notice this note at the bottom. It is recommended that you rerun the predictor after rescoring pathways, or if the knowledge base has undergone changes in pathways and protein assignments. And that's because part of what's involved in predicting transcription units is looking at whether multiple genes that are adjacent to each other are also involved in the same pathway. Now, we'll refine again with the transport identification parser. And what this is doing is it's just looking through all of the protein names for candidate transporters and trying to figure out if you may have transporters in your organism so it can start attaching transport reactions to them. And it will just keep track for you at the bottom of the page here how many candidates it's looking through out of the total candidates it has. So it has 127 candidate transporters to look through right now, and we're at about 45. So it's a pretty fast process. Okay, so now we get this probable transporter table, and these are high confidence predictions where it thinks, yeah, I really have found a transporter. And what we need to do then is go through and review all of these. And in the same way, well, similar to what we did before with reviewing possible enzymes, we left click here. It tells you a bunch of things, and you can accept, reject, defer, leave it alone. I'm just going to go through and accept these. And so I'm going to go through and accept the rest of these, and then we'll come back and look at what we do next. Okay, so I went through, accepted all of them. I'm being very accepting today. You don't, of course, necessarily want to accept all of them. You'll actually be looking at the literature, relying on your expertise on this particular organism, etc. Now we've completed transport identification parsing. Refine. Other than that, we can update the overview again. Before we do that, let's just go through and be cautious and save the KB. It's good to save every so often. And now that we've saved, let's look at refine again. We can update the overview. Let's do that. And of course, it'll bring up this thing saying, are you sure you want to upgrade the overview? There can be delay of an hour or more. It's not telling the truth. The delay is usually of 5 to 10 minutes. We just like to be cautious. And I'm going to say yes. And we'll come back once the overview is done updating. Okay, so now we have a sort of draft version of our model organism database. We've taken our GenBank annotation, fed it into pathologic, predicted gene products, predicted reactions, predicted metabolic pathways, predicted transport reactions, or more accurately identified transport reactions, predicted transcription units, associated compounds for the reactions, etc. We have our draft database. Now we go on to the next step of the pathway hole filling. Now the stuff you've done so far should have gone pretty fast. It went pretty fast for us, as we've seen. The pathway hole filling step is the step that takes a little longer. It's more of the set it up and do other stuff while it's running kind of step. It won't take forever, take a couple of hours, but it's not a sit and watch step. There'll be some manual things you're going to want to do at the end. But between starting it and the end, you're just going to walk away from the computer or run it in the background or do whatever. Okay, so once again, we're on our database here, Coxiella burnettii, and we're going to go up and click on Tools and start Pathologic again. Just maximize that. And we're going to click Refine, go down to Pathway Hole Filler. Now you see here we have 3 options. The 2 I'm going to focus on here are Fully Automatic and Wizard. Fully Automatic is if you're just willing to accept a bunch of cutoffs, you're just going to take what it says. You don't want to manually look at the pathway hole filling. You probably don't want to do that in most cases because you're probably doing just the one database for the thing you've just sequenced and annotated. You've done months of work on it. You're going to want to take a little time. So then you're going to want to use the wizard setting, which will kind of walk you through this. There's also the power user setting, which can be helpful if you've had to stop in the middle of the process or just you find you're a more advanced user and you want to tinker with individual steps. But we're going to choose wizard right now. So now we get this neat dialog box that tells us what we're going to do. It's going to tell you that the wizard consists of 3 main phases. We're going to plan, then we're going to perform our pathway hole filling, then we're going to review the predictions and decide which predictions we want to keep and which we don't. And as you'll see when we get there, it actually gives us a list of predictions for a given pathway hole. We might have no predictions, we might have 1 prediction, we might have 5 predictions that beat a minimum quality cutoff, and then we'll be given a score for each one so we can decide, well, this is the highest scoring one, I like it, or maybe in some cases this is the second highest scoring one, but for reasons of my personal expert knowledge about this organism, I believe this one instead. I'm going to take that. So now that we've read this, let's click OK and go on to planning the analysis. Okay, so it says required blast protein data is missing but can be generated now if you wish. This process takes on the order of an hour. So we're going to need to do this. We're preparing blast protein data. Click on that. Okay, so it says choose known C. burnettii Dugway 7E912 reactions to use for training data. And that's known reactions are those reactions that have an enzyme assigned. So basically it's going to look at our set of reactions where we already have an enzyme assigned to that reaction, and it's going to use that as its training data set when it later goes along and starts blasting stuff back against our genome to work out other predictions for the pathway hole filler. And again, if you want the full, detailed, less kludgy explanation of how that works, you want to look at our publications. They're listed on the website. So here you have the option of selecting all, deselecting all, or entering a number of items to select at random. Now let's just click deselect all, and that clears everything. Now I had it set to select 100 items at random, but let's just select all. Let's be thorough. Okay. And then I'm going to hit OK, and this is going to choose these known reactions. It's going to use them for making our blast training data set, and that is, as it says, going to take on the order of an hour. And it's on the order of because we let you choose how many. You might pick 400, you might pick, well, 10 would be a bad idea, but you can pick anywhere in the range. Okay, so I'm going to click OK and let the process get started. Then it's going to ask me to choose a set of pathways or reactions to make predictions for. Basically here you can go with all pathways with holes, which is what I recommend if you're making a new pathway genome database, or you can select the pathways from a list or select the reactions from a list. And that's if you are going back maybe and doing refining and you just have one or two pathways you want holes filled for, just one maybe, or a couple of reactions, maybe you've updated some things, you have reactions, you'd like some predictions just for those reactions, you can do that. But for now, since we're making a new database, we're going to go with the pre-default selected option, all pathways with holes, and say OK. Then it tells you when you click OK, the wizard will identify and evaluate pathways to fill pathway holes, and this could go on for a while. And at the end of this, you'll be prompted to review the predictions. So I'm just going to click OK and then let it run. And we'll come back once it's finished running and take a look at what we're presented with. And you'll notice as it's running on your machine that you'll have a progress bar. It'll show you what it's doing. It'll tell you what's going on. You can hit cancel if you need to. We're not going to do that now. We're going to let it run, and we'll rejoin this process once it's run through, and we can start evaluating and deciding which one of the pathway hole filler predictions we want to keep. Okay, so now Pathologic is done making its predictions, and it's time for us to go through them. You'll notice at the top it says minimum probability cutoff, 0.9. You can actually set that probability cutoff higher or lower. Once you've played with it, you'll get a feel for sort of what level of probability you trust from Pathologic. And you can redo the display to show things after you set the new cutoff. In our case, we're going to stick with 0.9. It's a good number. And now we have an option right up here at the top to fill hole with top candidate for all of them. That means you just take Pathologic's best guess for every single candidate. Now that's useful if you're trying to do this in a high throughput fashion and you don't really feel like manually examining every single candidate. In this case, since we're thinking more along the lines of making a database for our specific organism we're researching, we're going to look at each candidate individually and decide whether or not we like them for that spot. Okay, so you notice our first two here say show sole candidate. It means that Pathologic at the 0.9 probability cutoff or higher has only picked one candidate for each of these. And in this case, it's actually picked the same one, put A, to carry out these two different, but as you can see, highly related reactions. And so even though there's just one candidate, we could ask it to show that candidate by clicking here. And what we get is this display about the candidate. And it's going to show you a couple things, like it's going to show you the pathway hole that you're filling, this activity here, this activity here. It's going to show you what the candidate hole filler is. In this case, it's this put A proline dehydrogenase, delta 1 pyrroline 5-carboxylate dehydrogenase activity for put A. We go down here, it says what it thinks the probability is in this case, which is 1. It shows what the gene reaction schematic looks like for the candidate right now. You can see that put A is already carrying out a lot of reactions, but there are a lot of related reactions. So it might make sense to add one more on. You can scroll down, average rank, best E value, shotgun score, average fraction aligned, etc. So if you want to know what the nitty-gritty stuff down here means, again, I recommend looking at the paper. Now let's flick back up to the top here, and also you can click here for definitions of what the different rows mean if you don't feel like going to the paper. So now we can see our hole filling options here: no, yes, and yes by replacement. I'm just going to close this and say OK right now because we have those options on the main screen too. Now, what does it mean to treat a pathway hole filling candidate in this fashion? Well, if we say no, it means that despite Pathologic's confidence in its prediction, to anthropomorphize a little, we don't believe it, we don't want to include it, we think it's inappropriate, whatever, no. Yes by adding function means we think that the protein in question does everything it was supposed to do before, plus the new predicted function from Pathologic's hole filler. Yes by replacing function means that we think the pathologic hole filler prediction is actually more appropriate than the current reaction that is attached, or reactions, plural sometimes, to the protein in question. And that might happen if the original activity that was assigned to the protein was either too specific or insufficiently specific. And that can happen by differences between how people annotate things versus what you personally know. They may have given something a vague annotation in the GenBank file, and now you go through, but you know this does a more specific version of that activity, so you actually will replace it with what the hole filler came up with. So in this case, we'll just say yes by adding function, yes by adding function. Now here, for this reaction, we can see, and this is part of isoleucine degradation, we have a couple in a row from isoleucine degradation, we can see that we have multiple candidates. So in this case, we can say, show me all the candidates. And it shows you the pathway hole. And then I scroll down, and we have all the candidates in rows like this. And we have the probability, and we have the probability of 1 for the first candidate that was suggested, and we have probabilities of 0 for the others. Now, that doesn't necessarily mean that they're inappropriate candidates, though. In this case, it means pathway hole filler thinks this is the most appropriate candidate. Let me flick back up to clear that. There we go. But if you actually look, and this is the value of it showing you all the things that scored high enough, you have PDHB, PDHAB, and another gene that doesn't get that PDH name, but which is a putative beta subunit, alpha-beta fusion protein. In other words, pathway hole filler has picked what it thinks is the best one for you based on its methods, but you, as the manual curator, can look and see that these are all high scoring for a pretty good reason. It looks like they may all actually carry out this activity. And so in this case, we can actually just say, yes, add the function, yes, add the function, yes, add the function, just across the board, and accept all of them. And so we can flick down through the others in the same manner, and we have things like UDP glucose conversion, mandylate degradation, and again you'll have sole candidates or 3 candidates, etc., etc. And you may end up with quite a few of these to work your way through. It depends on the size of your database, the effectiveness of the blast, etc. It's really hard to say. In this case, we have up to 4 candidates for the UDP glucose conversion. I've handled hole filling incidences in the past where we have 43 good scoring candidates for a given activity. Then you have to decide how many of them you believe and how many of them you want to include, or if just one of them is the appropriate one. Now, of course, the value here is that this can actually, as I think I mentioned at the beginning, feed back into your annotation. This is another way to take a stab via sequence and other based prediction methods at what gene functions may exist in your organism. And it leverages the strength of our having already made a preliminary database for your organism and assigned reactions and predicted metabolic pathways. Because once you have a good guess that a pathway, say UDP glucose conversion, exists, then it's a fair bet that there should be things carrying out the steps in the pathway we haven't yet assigned, and it's also a fair guess then that they will be similar to things that we already know that carry out those pathway steps. But it's a really nice way to take an annotation you've gone through maybe over and over again using current annotation tools and add another layer on top of it based on the strength of guessing what its metabolic complement overall looks like. Okay, so in this case I've only picked a couple, but it's enough of a demonstration. And I'll just hit Save Selections to Database. Yes, I want to fill all the selected holes. And it does that. Then I'm going to go up to the top here, set everything that's left to yes, fill with the top candidate, then save again. Then hit OK. And this puts us back in the general pathologic view. And I'm just going to one more time, because I'm careful like that, save the knowledge base. Okay, we've saved our database. Now we've added in a number of reactions. And what this means is we want to do another refining step. Let's rescore pathways, and then we're going to rebuild the overview. And then I'll move on to part 2, where we talk about editing your brand new pathway genome database. Okay, we've rescored pathways. Final step. Let's rebuild the overview. And we'll, of course it asks me again, am I sure? I am indeed sure. And while the overview is rebuilding, you can go away, come back, and in part 2 we'll take a look at our shiny new pathway hole filler predicted model organism database and the general process of editing a pathway tools database with a specific eye toward editing your brand new database. Okay.